Hello learners, hope you have a fine day. In this video, I am going to discuss about tuning of the PID type of the controller, that is proportional, integral and derivative control. So the contents are introduction to the PID controller and the technique used for tuning of the PID controller. So let us consider the simplest control system. Within this, we are having the set point and we are having the output over here. Output is being fed back through the feedback link so as to produce the output between the reference input and the actual output. The error signal is being given to the controller that is producing the actuating input on the actuator, and that actuator produces the input that is to be applied on the process so as to make up the desired output as the actual one. So what is PID type of the controller? It works in three ways. It produces the control action proportional to the error between the actual and the desired output. Then second is the integral action that keeps into account the integral of the error. And the third one is the derivative of the error. So why it is so? Because if we simply use the proportional type of the controller, we cannot increase. If we keep on increasing the proportional gain, the steady state error keep on reducing, but there is a particular value of the gain beyond which if we increase the value of the gain, the system response will become oscillatory. So we cannot increase the value of the gain beyond particular value, so we go for the other elements within the controller, which are the integral and the derivative one. Then sometimes during the at the time of the starting, as we have said, when we increase the value of kp, the system response becomes oscillatory. It means that rate of change of the error becomes quite high when we are using the proportional control only. In order to keep those oscillations at a less level, we use the derivative control, which produce the control action proportional to the rate of change of error taking place. More oscillations means more rate of change of error, means more action given by the derivative control. But proportional and derivative control, it means that derivative control is simply improves the transient portion of the system response. But if we talk about the steady state error, then both proportional as well as derivative control will not be able to avoid the steady state error. So in order to make up the steady state error as minimum as possible, we have to use the integral control, whose control action is proportional to the integral of the error. Because in case we just take into account the instantaneous error, like in the case of the proportional and the derivative control, that error becomes very less as the steady state is reached. So the control action of P and D type of the P and D component of the controller, that becomes quite less. So that cannot bring system to working to the desired set point. So in order to bring the system to the desired set point, we require a certain controller that can take up the integral of the error. So that is the integral control. So it means that three part of the PID controller are proportional controller, integral controller and the derivative controller. All these controllers are added up together so as to produce the actuating input on the process, so as to make up the actual output as the desired one. Then PID controller are everywhere due to their simplicity, and they are used in more than 95% of the closed loop industrial processes. When we talk about the tuning of the PID controller, tuning means there are basically three parameters within the PID type of the controller, that is KP, then we are having KI, then we are having KD. And this can also be written as equal to KP into 1 plus 1 divided by TIS plus TDS. This is the another form of writing the PID type of the controller. So whatever form we are taking, we will be required to tune three parameters. So KP, TI, and TD. So PID controller is one of the most commonly used control topologies in industry, reaching 94% of the control loops, and it's not having any need for knowledge of the system model. And a well-tuned controller is able to have good load disturbance rejection, little noise influence, good tracking response, and limited rate of variation. Then how do we tune the PID controller? For that, uh, we uh, we are using a number of the technique, and the most popular technique that uh, we use, that is the Ziegler-Nichols tuning method. Then how do the PID parameters affect the system dynamics? That we can very well see. If we uh, uh, if we increase the value of Kp, then rise time decreases, overshoot increases, settling time is not uh, no definite trend, and steady state error decrease. Then because of the effect of increasing Ki, the rise time will decrease, overshoot will increase, settling time will increase, and the steady state error will eliminate. And because of the derivative effect, this is for rise time, there is no definite trend. Overshoot will decrease, settling time will decrease, and steady state error is not affected by the presence. So we can very well see from here that because of the presence of the integral control, the steady state error will almost eliminate. And because of the presence of the derivative control, the overshoot will decrease. So derivative control improves the transient response, and integral control improves the steady state response. Then typical steps for designing a PID controller are: determine what characteristics of system need to be improved, use Kp to decrease the rise time, use Kd to reduce the overshoot and settling time, use Ki to eliminate the steady state error. So obviously we have to see, we have to look up at the application, and depending upon them, we will decide the value of Kp, Ki, Kd. So in order to get the tuning of the PID controller, means in order to get the three parameters of the PID controller, that is the proportional gain, integral gain, and derivative gain. The most classical method that is used is the Ziegler-Nichols tuning method. So the first method is the S-shaped step input response curve method. So within this, this S-shaped reaction curve, it can be characterized by two constant: delay time L. So this is the process. This is basically the input response curve. So it is giving you the response of the system uh, with respect to the time. So you can very well see over here that L is the delay time. This is the shape of the curve. Then we at a point of inflection of the curve. This is the point of inflection. We just draw a tangent and we find out its intersection uh, uh, with the time axis and this steady state level line. We are getting 2 points. So that will give us the value of L and the value of T. So if we are using the Ziegler-Nichols first method, then the value of Kp will be kept as equal to T by L. And this one for the proportional controller, Kp will be kept as equal to T by L. Ti will be kept as infinity, Td will be kept as equal to 0. In case it's a PI type of the controller, Td will be equal to 0. Kp will can be kept as equal to this, Ti can be kept as equal to this. And for a PID type of the controller, these are the various values for the proportional, integral, and derivative gains. So this is the Ziegler-Nichols first method, in which we simply just take up the output of the system with respect to the time. We draw the tangent line at the inflection point and get the value of L and T as shown in this curve, and then we this table indicates that how we decide the value of the various gains, and it generally gives the satisfactory response. Then the Ziegler-Nichols tuning second method. In this case, we start up with the closed loop system with the proportional type of the controller, and we just keep up the value of the gain as very small. Then we keep on increasing the value of the gain till a steady state oscillation occurs. Suppose this gain as equal to KCR. Such type of the oscillation will be produced in the system when we keep on increasing the value of the gain. Then gain estimator chart is, so this is the value of the gain. This is PCR. This way, this gain, that gain is observed, that gain is noted, that is KCR, and the distance between two troughs, that is that is noted, that is equal to PCR. Once we are having the value of KCR and PCR, then the value of Kp, Ki, and Kd, it is chosen with respect to by looking at the table that we have shown over here. And this method generally gives good results. And these are simply the rules which have been formed within the Ziegler and Nichols tuning methods, first and second one. We have, in both the cases, we have given you the table. And according to that table, if we decide the value of the proportional integral and derivative gain, then the satisfactory result can be obtained from that particular PID controller. So Ziegler-Nichols tuning method is used to determine an initial estimated set of working PID parameter for an unknown system. And usually it is included with the industrial process controller and motor controller as part of the setup utilities. Some controllers have additional auto-tune trains, and in addition, nowadays we are using the intelligent controllers for the tuning of the PID controllers, which take into account the uncertainties present within the system. So I think all of you have now become familiar with the process of tuning of PID type of the controller and Ziegler-Nichols method for tuning of the PID controller. Thank you very much for the patience learning. So I just stop over here. Thank you so much.